as a scientist myself, as a research scientist for 15 years before moving on to Group14 and leading the business development team here. As a scientist, you want a sample of everything you can possibly have a sample of. You'll say yes to any startup out there that's willing to give you a few grams of this new interesting technology that they have. Developing a material that can be successful with that knowledge, where they'll have success and it'll pique their interest if and when they do test that material. That's really one of the biggest challenges.
Welcome to Manufacturing Insiders. Today I have a highly credentialed guest with me today, Joel Meyer. He is a PhD in organic chemistry. He is really kind of leading the charge to developing new battery technology, with greater storage. As we all know, energy is a huge part of our lives, and the battery space has, it's made some improvements over the years, but they're really trying to revolutionize the amount of energy a battery can store. Welcome to Manufacturing Insiders, Joel. Looking forward to our talk.
Hi, Nate. Thanks so much for having me today.
Absolutely. So you have a PhD in organic chemistry. How do you end up in batteries?
I'll give you the short version because it's a bit of a meandering story. But so my PhD in organic chemistry, so it was focused on the synthesis of small molecules that can give us insights to how energy can be stored and how energy can be transferred. So it's very fundamental research, as a lot of academic research is. But the reality is that the learnings applied from that research you can draw a direct line through the various industries that I've worked in, aerospace materials and automotive and biotech. And you can draw a direct line of materials chemistry and the needs and the requirements, both physically and from an energy storage perspective, from this academic research into the energy storage space, and more specifically, battery technology.
Gotcha. So why is this important in your mind, to develop a material that increases the storage capacity of a battery?
Yeah, I don't think it's very insightful to say that batteries are an important part of everyone's lives today. I think the reality of the electrification of every part of our life has been steadily increasing, and more recently in the past few years dramatically increasing with the adoption of new technologies, the Internet of Things, the EV mass adoption. I could name a bunch of different industries, but the reality is that the need to store energy that we can create, and we can create a lot of energy,
right.
But the need to store that energy and then be able to use it as needed is just ever more important, both at the consumer level, but also at the large scale level, right? So implementation of thinking bigger picture, green energy technologies, whether it's wind or solar. Everyone's heard of the detractors making statements like, what happens when the wind stops or when the sun goes down. And really the solution to that is, one of the solutions to that is being able to store that incredible amount of energy that we can create without having to just burn stuff to access the energy.
Right.
That's fossil fuels or coal or wood or whatever you have.
Right. So functionally, what you guys have done is, in my research, the idea of introducing silicon into the graphite in a battery is known to increase the storage capacity of that. You guys are kind of taking a step further than that, right?
We're let's say in some ways combining those two concepts. So little bit of history. So for those not very familiar with the battery technology space, historically the anode part of the battery, so the part of the battery that stores lithium when your battery is fully charged, historically that has been a carbon-based material, graphite, and that's used to store that lithium. And then for basically the entirety of the lithium-ion battery history, that has been the anode that's been used. It's cheap, it's readily available, and it does a decent job of storing lithium. But what scientists like myself and people at Group14 have been searching to do is find a material that is functionally more proficient at storing that lithium, that has better technological capabilities, whether it's fast charge or discharge, or higher energy density. And so one of those materials that scientists have been researching for quite a while is silicon-based material, and silicon is an element that has a capacity, so the ability to store lithium it's 10 times higher than graphite. But there's a lot of challenges with using silicon materials, and so the cycle life, so the number of times that you can charge and discharge your electronic device or your EV. When you use silicon, historically, you've had very poor cycle life. Some of the other, we don't have to go into a technical deep dive, but there's other technology targets that you just haven't been able to hit. So what my company has done, what Group14 did, was develop a material that combined the stability of graphite, which you can get thousands and thousands of cycles with graphite, and that's basically what's in most batteries today. And if you combine that with silicon in a specific way, you can get basically the best properties of both of those materials. And that's what my company has done. That's what Group14 has done, is combine the stability of graphite, of carbon-based materials, with the higher energy capacity and higher power capabilities of silicon.
Very interesting. And so this, from what I understand from talking to you, this material actually can do what, 5 times the storage of traditional graphite?
Yes, exactly. Wow.
Okay. So the repercussions for that, for driving an EV, or obviously storing power from the power grid, excess power, huge. I mean, that's absolutely huge. Because that would make EVs a lot more of a viable solution, I feel, for a lot of people.
Yeah. So I think that there's really 2 ways that people look at it in the EV industry. One is that if you, so right now, the way that EVs are designed, you have a specific amount of space that's allocated for the battery pack. And that battery pack is responsible for how far your car can drive on a single charge. That's what gives you all of the power. Now, there are 2 things that you can do with a battery, let's say, or a material that facilitates a higher energy density. And one of those things is, within that same space, that same volume in the EV, you can put the same number of batteries. Every one of those batteries can store, however, 50% more lithium at the anode level. It's a bit more complicated. We don't need to get into the math. Let's just say 50% energy density boost, which is kind of the top end of technology today. And you can get a 50% energy density boost, meaning that your range is going to extend by 50% in that specific design. So that can be a huge relief for range anxiety that a lot of early adopters of EVs really experienced. And that was a real issue in EVs early on. But the other thing that you can do is, now that, there's a lot of EVs that the design battery technology has improved, and current packs allow cars to go somewhere, let's say 250 to 350 miles, depending on the design, the company, the goal, and the market. And what you can also do is you can use that higher energy density and say, look, I can already achieve 300 miles on one charge. I don't need my pack to be that large. If I use a higher energy density battery, I can reduce that pack size, making your vehicle lighter weight, reducing the number of cells that you have to integrate, while still maintaining that performance. And with silicon-based materials, you can get other higher performance, like fast charging, consecutive fast charging, that consumers really like, that will also facilitate that an easing of the range anxiety that's been a traditional detractor of EV adoption.
Right. Yeah, that's amazing too, to think that not only can you increase the lithium storage capacity of the battery, but you can also kind of deal with that issue of those lithium ions getting trapped over time and losing the capacity of the battery.
Yes, exactly. That's one of the amazing things about silicon. So, I'm a huge advocate for silicon, and I'm not going to, I'm biased here working in the space, but I think the reality is that after decades of incremental improvements in batteries, the reason I got into specifically into the silicon space is it was the technology that made the most sense to me. It
Hmm.
was the technology that was closest to implementation, to really having an effect on a market or on many markets. And I thought that the design and the technology at Group 14 was specifically the technology itself and the vision of manufacturing scale up. The strategy around that was just something that I thought was missing in a lot of the next generation technologies that exist out there. But I mean, the opportunities for silicon, with every let's say every technology is going to balance. So with all technology, you're going to, for example, with silicon's ability to store. So elemental silicon is able to store 10 times more lithium than graphite, but you'll also have a swelling of that material that's higher than graphite traditionally. And that's really been a problem for people trying to implement, for cell designers trying to implement this technology. Um, Group 14 has done a number of things to mitigate that observed swelling, which has led to some pretty rapid adoption across a number of industries. But the reality is I think silicon both facilitates that higher energy density. You can get that fast charging and that fast charging capabilities, as well as some other technological advantages. And where Group 14 has excelled and really led the industry is we figured out a way to do that while mitigating some of those other the other challenges that silicon has traditionally faced.
That's fascinating. Um, so there's several different ways I want to branch off of this, but I've heard a lot of I've talked to a couple people that are really innovating in the material science space using AI to kind of iterate in a much more efficient way. Are you guys kind of adopting that philosophy, or is this all like by hand kind of chemistry kind of stuff?
It's a combination of both. In any material space, I would say if you're not currently using AI in some way, then you're years behind right now,
Right.
because there's just not really an option today for this type of efficient or to research efficiently without at least having AI being a part of that process in some way to whether it's ML based modeling for next generation materials, or how a specific design may function in in a cell that you have not built yet. Building batteries is an expensive and difficult process,
Mhm.
and so you being able to use AI to facilitate a more efficient research process, it's just a no-brainer. But then the reality is that AI is never going to be 100% correct, and that at any point in time, 20 years down the line, we can have the best programs possible, and chemists are still going to be necessary. Material scientists are still going to be necessary to actually make the stuff and to then test it out and to iterate on those cells that AI may or may not be helping you to design. But I think the
Right.
reality is that yeah, we at Group 14 we are using AI. We also have a very robust research team to then actually iterate chemically and physically on what we learn from both on all literature and our own scientific brains, but also the kind of 4D capabilities that AI can really facilitate.
Yeah. I find that topic really interesting. I was thinking back to it was actually a very recent podcast we did with a guy who's the president of a company called Aries Materials, and they're developing novel polymers to, that can really have any function you want, like high strength, high temperature resistance, and they're almost entirely developing these materials with these language models that they've built and optimized for that specific process. But I just thought that was really interesting. There's a lot of challenges in that. Obviously, the data inputs that you need to build a model that works are huge. But no, that might be an interesting one. So I guess when you guys, so you have this material and you've already, I think when we talked originally, you said you captured 95% of the battery market in terms of, I guess, getting it into the validate, kind of getting your foot in the door, right?
Yes.
Can you explain that a little bit more?
Yeah. So we are engaged with 95% of the battery market. So by volume, 95% of the global battery manufacturing market, we have active programs with, and those programs can span everything from early stage testing, just validation of our technology. Can our material do what we say it does? All the way to SOP, where our material is the first silicon carbon composite material, so silicon-based material that's been implemented into large consumer electronics. We've got our material is in millions of cell phones in Asia. We have an SOP that we have announced with our partners. So ATL has made millions of cell phone batteries and electronics batteries using our material that are in the market. We also have a partner, Molicell, Moly Quantum, that makes cylindrical cells that are used in the EV industry, more niche EV, so like hypercars, F1, that type of application. There's some really cool YouTube videos that you can see that use our technology with a company called Mercury, which is a very niche hypercar maker that based out of the UK, that has a car that's won a number of different records for speed and power based on these Molicell cells that use our technology. And so we're in SOP with a number of companies, some of the more the company for OEMs that are looking to really push that boundary of the technology in their respective spaces, and are at times willing to take on a bit more risk with new technologies. But we also got very well established programs with various large OEMs that you would recognize. Porsche, we have a public relationship with Porsche, as well as pretty much every battery manufacturer and automotive OEM in the world.
That's very impressive. So I guess just from a high level, like how do you go from, okay, we've developed this innovative material, it works really, really well, we know it works well, and then we need to get these OEMs bought into it. Like what's that step? How do you do that?
Yeah, that's a difficult part of the process, and I'll give you a couple of reasons why. So the interesting part of actually getting a new technology implemented at the OEM level is not getting a research group at some OEM to say, oh, okay, yeah, you've got a new material, a new interesting technology. Sure, I'll take a sample of that and maybe I'll test it one day. As a scientist myself, as a research scientist for 15 years before moving on to Group14 and leading the business development team here. As a scientist, you want a sample of everything you can possibly have a sample of. You'll say yes to any startup out there that's willing to give you a few grams of this new interesting technology that they have. The challenge is then, first of all, getting them to actually test it rather than just putting it on the shelf and then letting it expire. Right. And then
we'll keep your resume on file.
Yes, exactly. So the black box of just stuff that people say, sure, go ahead and send it my way.
Right.
But then getting them to actually test it, but getting them to test it in a way that they will be successful is also not as easy as it may sound. scientists love to just say, okay, like I know how to make a battery. I'm going to take this material and I'm just going to do the exact same thing I did with graphite with this new material, even though it's not graphite. And so, developing a material that can be successful with that knowledge, where they'll have success and it'll pique their interest if and when they do test that material. That's really one of the biggest challenges. And that's where, a lot of materials startups, where startups will tend to spiral and eventually fail is at that step. Let's say you've piqued the interest of an OEM or a cell manufacturer, and they give you feedback and they say, okay, we put it in this cell and we got XYZ results. That's not good enough. So I need this and this and this and this and this. And they give you a whole list of, 50 different targets that they're trying to achieve, that are every one of the targets are 50% higher or better than last generation's technology. And they say, you have to achieve all of these or we're not interested. And what a lot of companies will do is they'll go back and they'll say, okay, we have to design a perfect technology. We have to hit all of these targets with, this OEM or battery manufacturer's specific manufacturing methodology and chemistries. And by the time you get done developing that for that one specific potential customer, you've developed a material or a technology that cannot be broadly applied because you've pigeonholed yourself with this technology.
You've made it too customized for that.
Made it too customized. And so you see a lot of materials companies in the battery industry that can have really interesting technologies. And if you do things in a very hyper-specific way, you can get interesting results. But being able to keep in mind that you need broad industry adoption if you want to have a truly successful technology. You don't need a perfect technology. You need a technology that will get your customers to that next stage, that iterative or better, that large step forward in capabilities. And then you need to be able to manufacture that. And the more specific a technology is, typically the more difficult it is to manufacture.
So what is your response then to that internal lab that that gives you all these qualifications? What do you say to that?
Everything's a negotiation. That's the reality of that. And it's not easy. It's definitely a balance, keeping the attention of these huge multinational conglomerates in Korea or China or Europe or wherever that have been in the battery manufacturing space for decades. It can be difficult to keep their attention. That's why both the technology has to be good enough, but then you have to prove to them that, hey, this is not just an interesting science project. You have to be very regimented and aggressive with ensuring that you keep that contact going, and you can show some progress, but you can also show them, or you also make sure that they know that, hey, I appreciate that you want to hit all of these technical targets that, your management set out for you, but this is what I can do for you. And I am able to scale this technology. The farther I go down this rabbit hole with you, I won't be able to scale this technology, and it'll just be a non-viable technical, interesting, tidbit in the annals of history, basically.
Right.
Yeah. And I think that, scientists fancy themselves rational people. And I think good, correct communication and relationship building is really the key there, even though it is, even though it's a scientific implementation, like relationship building, trust building, and really being willing to have those difficult conversations where oftentimes as a startup, like Group14, you don't have the leverage to really make a lot of those arguments, but to just keep coming back and pushing is really the key there.
And I would assume it seems like this is what I would do anyways, but you'd also kind of make a business case to them and say, listen, you sent me all these targets, but even if we could only meet half of them, or, half of the percentage that you wanted on each of them, it's still going to make this much of a difference in, whatever they care about, right?
Yes, exactly. So my favorite thing to do, which is not always appreciated by the science teams that we work with, is as soon as I get a product person in the room, That's really the end goal, is to work with the scientists, gain their trust, show them all the capabilities, go through all that negotiation and the back and forth of, your material is not as good as you say it is. Oh, yes, it is. It's actually this other part of the battery that's failing. It's not our material. There's all those technical arguments that happen. But then once you get to a stage where they're like, the scientists are saying, yeah, this is legit. So we want to keep pushing. You get a product person from that from that manufacturer in the room, and they'll say, oh, you can do that? Great. Yeah. Okay. So here's how we envision this actually moving forward from a productization perspective, which is usually completely different than these research teams. The early stage research teams see their goals. The way that the goals are defined for those research teams are just completely different. So when you have a product person that can come in and say, oh, here's what you can do. Great. I have a product vision for this. That's viable. That's really when you go from that early stage, early technology implementation to now we've got something. Now we can move forward with this customer.
Right, because they understand the dollar figures. They understand the impact on the consumer, and so once they can make that case, all of a sudden it's like, yeah, the scientists are going to do what we want them to do.
And one thing to add to that is that the targets that are given to early stage new technology research teams, they're meant to be hyper aggressive. They're meant to go out there and see what is possible. But what is possible, your OEMs, if you can show that you can make every battery maybe not quite that aggressive, but if you can make a stepwise change in battery performance that makes your batteries 40% better. Few OEMs are actually interested in doing that in one fell swoop, right? They want to have a product implementation path that will say, okay, this year we're going to increase our battery performance by 10%. Give it another 12 to 24 months, depending on your industry, sometimes longer than that. And then we're going to increase it by another 10%, and then another 10%. So really the goal is not to hit those are super aggressive targets that the research teams are giving. That's to push them to see what the bounds of current technology really are and what you can potentially balance. And I think that's the difference in perspectives. Those scientists are trying to see what is the craziest, most amazing thing that I can do with all these new technologies. And that's not what the product teams are specifically looking for in most cases.
Why is it so incremental? Is it because there's, downstream effects to the overall product? You're going to have to change structures of the vehicle or, that sort of stuff?
I would say that there's a couple of ways I could answer that. The first, I'm just going to say cost. We're talking about any new technology. If it's truly new, if it can truly give, some sort of crazy boost in performance, is going to be more significantly, probably more expensive. Right. Whether that's because the COGS, the CapEx, the OpEx of actually developing that industry make it more expensive, or if it's just because, hey, we can charge this much because nobody else can make this material. One way or the other, that material is going to be more expensive for that OEM, that battery manufacturer. And the market probably just isn't there at that scale. Again, I'm talking, mass market. I'm talking, hundreds of millions of consumer electronics or millions of EVs. If we put a car on the market today that was 50% more expensive and had 50% larger range, then you'll have buyers there, but the average consumer is just not able to access that, right? So I think it's more of the perspective of stepwise product implementation especially with new technologies, as your industry is building and costs are coming down over time, it just makes rational sense to do it that way.
Right. You might have already answered this, but maybe I want to have it in a little bit more of a nice package. So what's a piece of advice that you would give to somebody, maybe maybe not specifically in the material field, but it could be somebody that developed a really innovative component or something else that they want to get in front of an automotive OEM, for example? What's a piece of advice you give to that person we're kind of taking it from, all right, I have this idea, I made some steps towards developing it, what do I do next?
My advice is that has to be done in with the with your advantages put at the forefront, but then with an ability to have a conversation around what the realities are. So I consider myself, I tell my team we need to be as the technical team, the group that's out in the world trying to implement these technologies, trying to engage with these OEMs. You have to be optimistically realistic. You need to approach these OEMs and say, look at what I can do, and here is how you can do that. But also, especially when you're talking to technology teams or product teams, you have to be able to have some of that realistic conversation around here are the limitations. Like, yeah, I'm going to give you my marketing pitch, yes, but I can also tell you some of the challenges that are ahead for me, but still why you should be interested in using my technology. And I feel like that's something that, especially in the battery industry, just isn't there. And because of that, and when I say isn't there, I mean a lot of these new technology companies want to go and just make absolutely wild claims. There was a recent publication in Nature Nanotech that was called "Small Batteries, Big Claims," where all these new technology companies are coming out and saying, "Oh, lithium-ion batteries are obsolete at this point in time because our new technology we've proven it, we've done it, it's done." And the reality is that most OEMs will not respond to that if you don't have a reality check conversation that you can have with them. And I've found that has made Group 14 and our approach to our discussions, our relationships, and pushing the technology implementation forward. That's been the real difference maker for us, I think, compared to a lot of companies.
Yeah, no, I like that a lot. And honestly, it's a concept I'm somewhat familiar with in sales. I'm trying to remember which book I was reading that this came up. But basically, it's the idea that when you get in front of somebody, and to use to use a term that applies here, to kind of take the negative charge out of the situation, you're just right off the bat knocking out, here's probably why you don't want to work with me. Maybe not saying it exactly like that, but it's probably too expensive for you, whatever. And so you doing that makes them automatically try to make the argument for you, right?
I wonder, what was the book that you were reading? Was it Never Split the Difference?
Yes, Chris Voss. Yes.
I'm also a big fan of that book, and that's honestly so my strategy when interacting with customers comes directly from that. I think that it's a fantastic negotiation strategy book, but I think there's so many more implementations, different ways that you can use that, applications that you can use that information. I think that's exactly one of them where I've applied that idea. Here is what I want. Here is what I need. And because we're both here, we both acknowledge that we're here for business reasons, even if we're both technology, science, science teams. But I'm going to take the air out of your negative perspective on, oh, here's another battery startup, a material startup that's making wild claims. I'm just going to say, you know what? Our material does swell more than graphite. You know why? Because it holds 10 times more lithium, and that's how physics works. And as soon as you acknowledge something that to a scientist is just so obvious, then you immediately gain that sense of trust, take the negative wind out of their sails, and can move forward with a significantly more productive conversation.
Yeah, no, that's exactly right. No, I loved that book. I got an audio and I've listened to it probably 10 times.
Me as well.
The thing about audiobooks is like you don't absorb as much as you do when you're sitting down reading a book, so I have to keep listening to it to reinforce this stuff. But no, I think that's a great book for anybody literally to watch or to listen to.
Completely agree. There's a
Yeah.
master class on it too. He's got a master class on basically the same topic that I think is just adds another layer of nuance, because just being able to see him and see some of the interactions that occur that
Yep.
you don't quite get when you're just listening or reading, I think is also very interesting.
Yep. Yeah, I actually in the same breath a lot of times recommend a book called Stories That Stick by a woman named Kendra Hall, I believe. Um, but so the reason why I read that one is I've always kind of felt like I wasn't a very good storyteller, and I realized how important it was to, to be able to create a connection, with your client, because people remember stories, they don't remember facts. But it does such a great job of breaking down the specific elements that need to go into a sales story or a founder's story, and various types of stories, and how to construct those so that they resonate with your audience. Great book, anyway.
Yeah, I'll have to. I don't have a pen and paper now, but I'll definitely want to write that down. I love.
Yeah,
One of my
I'll
favorite
shoot it
parts.
over to you. I think you would enjoy it.
Yeah. One of my
So
favorite parts of moving over into the business side of things is I've just always loved the storytelling aspect. Technical storytelling is something that I'm just passionate about. So
yeah,
anyway,
yeah, and this will help you construct perfect stories. Like a lot of times people tell an okay story, but if you would just put in a recognizable character into the story and mention somebody's name, yeah, this guy James I was working with, he's this younger guy that was really whatever, like building that character and
yes,
then reflecting his emotions. He was really frustrated with the problem that he was having. He'd talk to this person and that person and didn't work, and then I came to him, so then there was that moment, right? So like those are the elements that you need. But anyway, so so what are the limitations with silicon? um I would assume, without really knowing, that it's more expensive just in general and difficult to procure than carbon, right?
yes. So the short answer is yes. The industry as a whole is smaller than graphite or hard carbon industry. There's some big players out there all over the world, and the largest silicon producer in the world is a company called BTR out of China. They're very well established, but they make certain types of silicon that are, let's say, uh, not as advanced as what Group 14 makes. But along with the not as well established industry, along with the higher technical performance, you're going to have that higher cost. The material is inherently so it's a synthetic material. You have to manufacture it. It's not something that you can mine and then refine and then use, which
Mm.
is basically that's what graphite is. I mean, there's natural graphite and there's synthetic graphite, but um, both have a very, very low cost, and China's been dominating that market for a very, very long time. So when you move over to silicon, you have you have all of the high costs associated with a new technology that doesn't have a good industrial foundation. But then you also have the increased functional capabilities, so the fast charging, the higher energy density capabilities. It's inherently going to always be a more expensive material, I think.
Right.
But the reality is that at the specific capacity level, so the metric that is used in the battery industry for energy storage materials, your price can easily be equivalent or less than that of graphite. But then at the material level, but you'll also have cost savings in being able to reduce your pack size in an EV, or even more importantly, with new technologies, uh, you need batteries that have a higher functional capability. So not just energy storage, but the power capabilities of those batteries to be able to power things like AI being processed in localized devices. I mean, that's a huge power requirement that we've never seen before. So where your iPhones today might last, hopefully 24 hours with their current capabilities, as soon as you put AI into that phone, you have edge computing going from these data centers to your specific devices, which is already happening. your battery requirements, the storage capabilities, the power requirements, those graphite anode batteries are just not going to be able to sustain the needs of the electronics themselves. And so you need these next generation materials, and you're going to have to pay a premium to get that functionality at this moment.
Right. What are the core? What are the, I guess, ingredients? And that's a stupid way to say it. What are the? How do you make silicon?
So there's a couple of different ways of making silicon. So to make nanosilicon, the most common way of doing that, so nanosilicon being elemental silicon that is the diameter of the particles is at the nanometer scale. That is typically you have silane gas as your raw material, and there is a chemical vapor deposition is what it's called, methodology where you take a gas and you, in a very specific manufacturing setting using temperatures and pressures, you turn that gas into a solid that is in a controlled manner, and it makes nanosilicon. So it's in some ways, from a chemistry perspective, it's rather simple because you have silane gas that's being decomposed into silicon. So your silane gas is composed of silicon and hydrogen. So you're losing all of the hydrogens and you're making a silicon particle. So chemically speaking, it's rather straightforward. But the process to actually do so is not very easy. There's quite a few companies that have their own methodologies to do so, and really, there's Group14 is to date really the only company in the world that has proven the ability to scale that type of technology to truly industrially relevant scale.
That's fascinating. So where do you get silane gas?
So silane gas is it's a manufactured gas. So metallurgical silicon is mined. You can get silicon all over the world, but basically you mine metallurgical silicon, which is an impure ore that you'll get out of the ground, and then you take that and you put it through a number of processes to. There's a number of ways that you can synthesize it, but basically you take that silicon and you make it undergo a few chemical reactions that then will slowly decompose these complicated mixtures of different elements, and you can extract just the silane gas from that mixture of things.
Wow, pretty heavy lift. I was just trying to wrap my head on kind of like the availability, as the need for batteries increases, how much of this can we produce? Is it something we can almost infinitely do?
I mean, I always hesitate to say infinitely do, but can we meet the needs of the battery industry, even the most aggressive projections? Yes, absolutely. I mean, right now, for example, silane gas is a gas that is used in the photovoltaics industry as well. And so, a decade ago, when there was this big boom, the expected boom of implementation of solar, of OPVs globally, there was this huge buildup of silane gas capacity. REC Silicon is the world's largest silane gas producer. And then SK Materials is number 2. We have very close relationships with both of those companies. But they essentially built up tens of thousands of tons of capacity of silane gas, of which only a fraction is actually getting used because the aggressive projections of the solar industry just didn't grow as quickly as was expected a decade ago. So really, there's a ton of available capacity globally in basically every major manufacturing region that's just sitting there waiting to be used. And then there's other technologies, there's other potentials for scale. We at Group14, we acquired a company called Schmid Silicon, who had done exactly the same thing. They built up a silane manufacturing facility that essentially never started producing silane gas. And so the factory is built and it's sitting over in in Eastern Germany, just waiting to be used. And we're commissioning that factory right now in our planning for European manufacturing as well. So really, we are not specifically to harp on Group 14, but for the industry as a whole, there's myriad opportunities for accessing silane gas, and frankly in China as well, because of some of the increase in battery and other technologies that utilize silane gas. There's been a huge increase in silane capacity coming out of China as well.
Okay. Yeah, and I'm sure there's a lot we could talk about around that too. But I know we're drawing to the end of our time here. But one last question for you. So I always like to ask, are there any resources you or your company are looking for that maybe somebody in the audience might listen and say, oh, that's me, I have that? Is there anything that you've been looking for?
Oh, that's an interesting question. I think that we're always looking for partnerships for, let's say, our technology being implemented into next generation technologies. So we're not a battery manufacturer, right? We make a raw material, and our material's ability to store lithium atoms is it really doesn't matter what that end technology is, and we let our customers and partners define that specifically. And so if we look beyond this current generation of battery technology of, let's say, lithium-ion or even solid-state batteries, where silicon is a very key player, really looking ahead at what those those leapfrog technologies and how our silicon materials can fit into some of these currently more exotic type of battery chemistries. That's very valuable for us, and we're always searching for new partners and new ideas on how our materials' ability to store lithium or something we haven't even thought of yet can be applied to these new technologies. That's really, I think, the biggest opportunity for listeners out there that would be interested in a hey, I've got something for you. I think that's really the biggest opportunity for us.
Okay, perfect. Yeah, and we seem to have a lot of these conversations recently around energy storage and energy in general. And so, there may be some connections to be made. But thanks a lot for your time today, Joel. You're an extremely intelligent, well-versed person in the space. And I also love the way that you think about, even your job search, getting to Group 14, kind of the way that you approach that, saying, the space that you wanted to be in and the stage of the company, like you were really analytical about that. I think that's really smart. But a lot of great advice to share. So thanks a lot for coming on today.
Nate, thanks so much for having me. It's been a lot of fun.